In this question, we're asked about the solubility differences between two different samples. So it says 250 milliliter samples of water are drawn from a deep well boring into a large underground salt deposit. Sample 1 is from the top of the well and is initially at 42 degrees C. Sample 2 is at a depth of 150 meters and is initially at 8 degrees C. Both samples are allowed to come to room temperature and 1 atmosphere pressure. An NaCl precipitate is seen to form in sample 1. So essentially what we have is we have a well. All around the well is salt, and then there's some water in the well. And we're looking at what happens to these two samples. Well, if there's massive amount of salt around this water, as much salt as possible will dissolve in the water. Said another way, you'll have a saturated salt solution. So there's two factors here that are changing. The first is the temperature. This one's initially at 42 degrees C, and this is at 20 degrees C. If it's at top of the well, presumably it's under some pressure, but not under a massive amount of pressure. If it's 150 meters down in the well, presumably it's under a much greater pressure. However, since the solute is a solid, the pressure doesn't have a great effect, so we're going to ignore that. So let's look at the temperature effect. In sample 1, we cool from 42 degrees C to 20 degrees C. So the water gets colder and we see a precipitate. Well, if the water gets colder and we see a precipitate, that means it was saturated at 42 degrees C where salt is more soluble. It cooled to 20 where salt is less soluble and a precipitate formed. In sample 2, it started at 8 degrees C and we actually warmed it up to 20 degrees C. That means we had a saturated solution at 8 degrees C where less salt is soluble, and we heated it to 20 degrees C. Since we warmed the second sample up, we're not going to see any precipitate. Because salt is more soluble at 20 degrees C, albeit slightly, it is still more soluble than it is at 8 degrees C. And when I say slightly, that's relative to some other types of salts where the solubility difference varies with temperature greatly. NaCl happens to be not a huge dependence on temperature, but there is certainly a dependence. Next question, a little bit different case. It says, a student has two unopened 33 centiliter cans containing carbonated water. Can A has been stored in the garage at 32 degrees C, and can B has been stored in the fridge at 8 degrees C. The student opens one can at a time. Both cans make a fizz. And then wants to know which one will have a stronger or louder fizz, or whether it'll be the same, or whether we don't have enough information. So in this case, we're looking at the solubility of a gas, carbon dioxide, and carbonated water, in these cans. Inside the can, the pressure is high, which keeps the carbon dioxide dissolved, just like in a can of soda or seltzer water or whatever that you've seen many times. However, here what's different is the temperature, because we're initially going from a high pressure inside the can to opening the can, which is a relatively low pressure. If the temperature is higher, the solubility of a gas decreases. So therefore, at 32 degrees C, the gas is going to be more readily escaping from the can than at 8 degrees C. And you could actually try this. Take a can out of the fridge, take a can at room temperature, open them up. Okay, you may be able to observe the difference in the fizzing. If you were to measure the time it takes the soda to go flat, if you wanted to do an experiment, you would find that it goes flat much faster at room temperature. This is a little bit higher than room temperature. This is like, you know, on a hot sunny day, but you get the basic idea. So in this case, the 32 degrees C can will make a stronger, louder fizz than the 8 degrees C can. So this is the answer here. In the last example, it says, a student sees tiny bubbles clinging to the inside of an unopened plastic bottle filled with carbonated soft drink. The student opens the bottle and hears a loud hiss as the gas under pressure escapes from the bottle. So this is like a plastic bottle of soda, essentially. And then it wants to know what happens to the bubbles. Well, if you take an unopened bottle of soda, you're not going to likely see too many bubbles in the soda. As soon as you open it, the bubbles start to come out. Why? Because you're releasing the pressure. the soda bottle is initially under pressure. Then when you open it, it's at atmospheric pressure, and the dissolved carbon dioxide comes out of solution. So what you'll observe, the bubbles will grow, and you may have more of them. In fact, you almost definitely will have more of them. So that's essentially 3 examples to answer this type of question.